Hello everyone, the Humble Math Tutor here. Today I bring you this very interesting math contest problem which has value in its analysis because it contains a recurring theme applicable in other problems. So it's well worth studying. It's not a one-off. Here's the problem. Given this quadratic equation, can you evaluate x to the 12th exponent? And we can. And the ride to the answer is very, very interesting. We're going to start by solving this quadratic equation for x to at least know what that value is at the outset. Here we go. So I've got this. X squared minus x minus 1 equals 0 solves to x equals 1 plus or minus root 5 over 2 with the quadratic formula. Now you might recognize one of these numbers, 1 plus root 5 over 2, is part of the golden ratio, which in fact is related to the Fibonacci sequence in a number of applications, including the solution to this problem. Now you wouldn't know that yet necessarily. You could merrily and happily just go right ahead with the algorithm I'm about to show you, but I'm just going to write the Fibonacci sequence down here because it'll be handy to have it written out for when it occurs in the middle of our algorithm. So the way to obtain the terms of the Fibonacci sequence is to add any two adjacent terms together to get the next term. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, 21 plus 34 is 55, 34 plus 55 makes 89, 55 plus 89 makes 144, and so on and so on. So those are the first 12 terms, as it happens, of the Fibonacci sequence. We'll be needing them, even if it's not evident yet. Now let's get started on probably the most important part of this presentation, and that is this algorithm, the recurring theme. What I'm going to do is I'm going to move the negative x and the negative 1 to the right, and that gives you this equation, that x squared equals x plus 1. What I'm going to do is I'm going to produce x to the 12th on the left side by multiplying through this equation by x over and over and over, building the exponent up on the left side up to 12. But every time I multiply by x, I'm going to obtain an x squared in the right side, and I'll immediately knock it on its head and replace it with x plus 1, keeping the right side linear while the left side builds up to x to the 12th. That's the genius of this algorithm. Here we go. Multiply both sides by x, and I get x cubed equals x squared plus x. But wait, x squared is the same as x plus 1. So I'm going to replace this with x plus 1. That gives us x cubed equals x plus 1 plus x. Simplifying, that gives us that x cubed is equal to 2x plus 1. Again, I'm now going to multiply both sides by x, and that gives us x to the 4th is 2x squared plus x. Again, x squared is equal to x plus 1, and that gives us x to the 4th is 2 times x plus 1 plus x, and that simplifies to 3x plus 2. So we're successful. We're keeping the right side linear while the left side builds up and up and up. Now it might seem kind of disheartening having to go all the way up to x to the 12th, but we won't have to because the Fibonacci sequence, it will actually come to our rescue and do the heavy lifting for us. Watch this. Allow me to make a few more terms though, all the way up to x to the 6th, please, so that the Fibonacci's appearance will become very evident. So I'm going to multiply both sides by x here, and that will give us the following. X to the 5th is 3x squared plus 2x. Replace x squared with x plus 1, giving us x to the 5th is 3 times x plus 1 plus 2x, and that simplifies to 5x plus 3. Again, multiply both sides by x just one last time, and that gives us x to the 6th is 5x squared plus 3x. Replace x squared with x plus 1, and we get x to the 6th is 5 times x plus 1 plus 3x. And that finally gives us x to the 6th is 8x plus 5. Okay, examine the coefficients of x in every simplified form so far. That's 1, 2, 3, 5, and 8. Those correspond to these numbers here, 1, 2, 3, 5, 8. In other words, the exponent being applied to x tells us the term index of the coefficient of x. So for example, this 2 means use the second term in the Fibonacci sequence as your coefficient of x. So that 2 says the second term in the Fibonacci sequence here is 1, and that becomes the coefficient of x. Try it again. So here, this is x cubed, and that says use the third term in the Fibonacci sequence as your coefficient of x. And sure enough, it works, all the way down to the last one. So for x to the sixth, we use the sixth term in the Fibonacci sequence as our coefficient for x. Well, let's check out what the sixth term in the Fibonacci sequence is. 1, 2, 3, 4, 5, 6. And if you do the same thing for the constant terms, which are 1, 1, 2, 3, and 5, you'll see those are these terms. In other words, the constant term lags 1 behind. So if you're using the second term of the Fibonacci sequence as your coefficient here, this is the first term of the Fibonacci sequence. And if you're using the third term from the Fibonacci sequence to determine your coefficient here, this will be the second term from the Fibonacci sequence. All the way up to the sixth term. Let's examine this now. Remember, the sixth term in the Fibonacci sequence determines your coefficient of x. The fifth term in the Fibonacci sequence determines the constant term. It's one term behind. So the fifth term is 1, 2, 3, 4, 5, and that's right here. So that gives us the following important generalization, that x to the n is equal to the nth term of the Fibonacci sequence times n plus the term from the Fibonacci sequence one prior to that. And that's our important generalization we can use now to jump immediately all the way to x to the 12 would be the 12th term of the Fibonacci sequence times x plus the 11th term of the Fibonacci sequence. Let's place those in position. What is the 12th term of the Fibonacci sequence? Well, no coincidence that I happen to write out the first 12 terms here. That's the 12th term of the Fibonacci sequence. That's the 11th term. So you can just plug them right into position here, and you would get that x to the 12 is 144x plus 89. But wait, x was determined at the start of the problem. So I can take that and plug it in now and simplify to get a nice, crisp, clean answer. And that gives us that x to the 12 will be 144 times 1 plus or minus root 5 over 2 plus 89. This simplifies easily. Let's see what it comes out to become. So the 2 in the 144 makes 72 times 1 plus or minus root 5 plus 89. And I'm going to run the 72 through against the two terms in this binomial, and that gives you 72 plus or minus 72 root 5 plus 89. And then 72 plus 89, what does that come out to? I think it's 161, I think, plus or minus 72 root 5. And that's the value of x to the 12. If you enjoyed this video, please like, subscribe, and share. If you have suggestions for future topics for videos, please leave those in the comments section below.